Okay, section 7.2 begins on page 390. And right in the middle of the page, it looks like a breaching whale,
It's like cloud.
right? Trying to get to the surface for air. Hey, listen, guys. This is just called areas in the plane. There's all sorts of things we're going to be doing here, and they should make good sense based on areas that we found before. But the first topic we're going to discuss is area between two curves. Instead of just area under a curve between the x-axis and that curve, we're actually going to find the space between two different curves. And you'll notice that in this breaching whale type thing, it looks like some of the, if we integrate from A to B, the distance or the area between them, most of the upper curve is above the x-axis, most of the lower curve is below the x-axis, but they've each got some of each, right? Well, it turns out this is a lot easier to consider and think about and handle than you think. All you got to do, and one condition, the upper curve has to be the upper curve throughout the entire region, and the lower curve has to be the lower curve throughout the entire region from A to B. If that's the case, and you think about this for a minute, all you have to do is integrate the top curve minus the bottom one.
That makes sense.
Even if some of it's positive and some's negative, and as long as they don't cross somewhere in the interval so that one becomes upper and lower and they switch places, as long as that doesn't happen, even if you've got some negative area for one of them and becomes positive, and it's all handled in the positive negative with the minus. Because you'll be subtracting a negative in certain regions, yes.
So if there was a cross, would you integrate from like A to the cross and then on the other side of the cross to your B?
Yep, and you have to find the intersect point algebraically. That's one of the reasons we found intersect points. One of the reasons, there's many others, but yes, that's what you would do. You would split it up into two integrals and they would switch places in the subtraction. So the top one minus the bottom one is the key. And if they switch places, then you're going to have to stop integrating where they cross and do the top minus the bottom for the other one and add the two together. You see what I'm saying?
Cool.
And we're talking about actual paintable space, the whole whale here. Some of it's below the x-axis, some is above the x-axis. It's all taken care of in the minus. So we all have to do, if the top one is f and the bottom one is g, then all we have to do is integrate f minus g. And that's what's told to you down there at the very bottom of the page in the tan box. And it has a big if in front of it. All these things do. But let me just reiterate and summarize. It says if f and g are continuous, where f dominates g throughout the interval, then the area between the curves, f and g, from A to B, is just integrate f minus g from A to B. And that will be area, not an integral, that will be area between the curves. Thinking about painting it. Doesn't take into account the negatives, okay? So take a look at example 1. It says, find the area of the region between secant squared and sine from 0 to pi fourths. And they've got a graph out for you over there on the left. Can you see the sine curve coming up through the origin? And do you remember what secant looks like? Secant is made up of a bunch of scallops. Secant goes like this. Well, I guess I better get over here. Secant goes like this, and then like this down below, and then like this, and then down below. If you square secant, it kicks them all up top and changes the shape just a little bit. But they're all scallops on top. Okay, so secant squared up there it dominates the sine curve throughout the region from 0 to pi fourths. As a matter of fact, it dominates the sine curve everywhere except for where they meet. They meet periodically, sine curve. Okay? No, do they? Anyways, can you see why they would have chosen to use secant squared though instead of just secant? Yeah. Secant squared is somebody's derivative. It's real easy to antiderive. And so using the thing we just learned to find the area between these two on the interval from 0 to pi fourths, you just go 0 to pi fourths and you do the top one, the one that's dominating, one has the higher y values, which is secant squared minus sine. And you integrate them separately. So it actually becomes the integral of this, both evaluated from 0 to pi fourths. We can do it all at once. What's the antiderivative of this term? Tangent. And the antiderivative of this?
Cosine.
And so do I keep the negative sign?
No, you have
Do I?
Plus cosine.
Plus, isn't it? Because when you antiderive sine, you get back to cosine, but cosine's derivative is not sine. Cosine's derivative is negative sine. So we got an extra negative in here. Y'all see it? Okay. So cosine evaluated from 0 to pi fourths. What is-
Potentially, could you mint this?
What?
Potentially speaking, could you just mint?
Of course, but we don't do that. We don't have to.
Okay.
When they design this for us to be easily antiderivable, we do it.
Okay.
Okay? We're not going to default to that all the time. It turns your brain to mush. What is the tangent of pi fourths?
Root 2 over 2.
No. Tangent of pi fourths.
1.
1. Because we are in a 45, 45, 90 where the legs are the same length. And so it's opposite over adjacent, which is 1. You following? What's the cosine of pi fourths? No. Oh yeah, I am evaluating. Yeah, I'm putting pi. Okay. So plus root 2 over 2
Yeah.
minus. What is the tangent of 0? 0. What's the cosine of 0? 1. So it's root 2 over 2.
Wow.
You see it?
Yes, sir.
Okay. All right. So that's example 1, applying that thing we just discussed on page 7.2. We would do exploration of family butterflies. It sounds so fun. So we're not. Look at example 2 instead. Example 2, this is one where it's not just handed to you. Not just going to be handed to you the way this one was, where you just do top one minus bottom one, and they tell you to go from 0 to pi fourths. This one, they want you to find the area between two curves, which means you're going to have to find the limits of integration. So in example 2, it says find the area of the region that's enclosed by the parabola y equals 2 minus 2 minus x squared and the line y equals negative x. If you don't know what those look like, you can put them on your calculator. Since I'm giving this lecture on tape here, I'm going to graph it for you just so that we can point to it. We can do both of these things. We ought to be able to graph by now without too much effort. It says 2 minus x squared. Can you see that that's an upturned parabola that crosses the y-axis at 2 with a normal opening? So I would start here and I would go out 1, down 1, and I would go out 1, down 3 on the other side as well. That would be my parabola. And then I've got the other one as a line that crosses the y-axis at 0 because there's no y-intercept, and the slope is negative 1. So it's going to be a line that goes like this. And we wish to find this space enclosed by the 2, which means I'm going to have to find this x value and this x value. Now, is it fairly clear to you because of the graphing that this is negative 1? Seem reasonable? Okay, well, we need to find this other one. If we didn't have our calculator, just pretend we did it for a minute, how would you find these intersect points? This one came from the graphing. This one may not be quite so clear, or maybe it is. I don't know. But I need to find these two because that's where I'm going to from here to here where this dominates this curve, and I want to find the area in between. So how do you find them? How do you find where they cross each other? This equation and this one. What? You set them equal?
To each other.
Because if this y equals negative x, this y also equals negative x, right? That's what we're trying to find is when they both have the same. So I would go negative x equals 2 minus x squared. Since this is negative on this side, I'm tossing everything over here. Vx squared minus x minus 2. Does that factor? What goes back here? 2 and 1. Which one's negative? The 2. So that's thing. This has x values. They share x values at 2 and negative 1. There's my negative 1. That's a 2. So I'm going to integrate from negative 1 to 2 based on the graph. But you have to find that out. So we will integrate from negative 1 to 2. Which one dominates in this case? 2 minus x squared minus negative x. Top minus bottom. You okay with that? Got a little cleanup to do before I want to integrate. That's going to be 2 minus x squared plus x, which is negative x squared plus x plus 2. And I want to integrate that from -1 to 2. Just cleaning it up a little bit. What's this one's integral? I'm gonna, that's a little too close. 2 minus x squared plus x. Okay, so now I'm down to this integral. This is gonna be what?
-1/2 x squared.
Really?
1/3.
Oh, no.
What does it?
Oh, it's so embarrassing.
It is.
No.
-1 to 2. Let's see how good you are at arithmetic. This is gonna be -8/3. This one's gonna be 2. And this one? 4. Minus. What's this one gonna be if you plug -1 in? No, it isn't. 1/3. Just 1/2.
Yeah.
Okay, now let's see how well you do with this. This is 6, right? Which is the same thing as 18/3,
That's what I would say.
right? 18/3 minus 8/3 is 10/3, so this one turns out to be 10/3. This one is 3/6 plus 2. No, sorry. This one is 2/6 plus 3/6. We got 5/6 minus 12/6. 5/6 minus 12/6 is -7/6 plus. That's 26 plus 7/6. Both have a 3. That's a lot of arithmetic. You can do that in your head. You can do that in your head, or you can do that in your calculator. You can even do this with your calculator if you want to let your brain go to mush like Kyle does all the time. No, I'm teaching Kyle, but yeah. If you can integrate, you should practice it, because there will be parts of your final exam where you're not allowed to use a calculator, so you should practice it. Okay.
Not even to check your
Pardon
answer.
me. Okay, so that's what happens when you gotta find your own limits of integration. You set the equations equal to each other and find the x's that they share. That's what you integrate from the 2. All right, example 3, same situation, only this time it's not so cut and dried. It's not so easy to deal with. It's not so easy to graph these, and it's not so easy to find the intersect points as it was here. So we're gonna do the same thing again. We're gonna make our calculator do the nasty stuff. So
Yeah.
those calculators handy. Are you all familiar with the storing aspect of your calculator?
Yeah.
Because you're going to use that so that you don't have to sacrifice any accuracy until the final answer. So, okay, so in example 3, it says, find the area of the region enclosed between the graph of y equals 2 cosine x and y equals x squared minus 1. Y equals x squared minus 1 is an up, is at -1, and 2 cosine x near the origin, at least where it's going to encounter that parabola, is upturned coming down. So you can see the graph to the left. You can graph it in your calculator too, and you should, because we need to find the intersect points, and that's where we find it in the graph. So make sure you're in radian mode. Okay, so the positive intersect I get looks pretty irrational to me. The positive intersect x value is 1.2654237, yeah? I want to show you something that you may want to use in the future so that you don't have to store 2 values. You can, if you want. It's fine. Store 2 values if you like. But if you've got 2 things like this, and that happens more often than you think. You got 2 things like this that are symmetric. Y-axis symmetry. Both of these are. That was 1, 2, 6, come down 1. Is it cross on the x-axis or is it somewhat above it? It's a little above it? Okay, so it comes like this and does this kind of thing later. Okay, and we're trying to find these x values right here. Because we know that cosine and this particular parabola have y-axis symmetry, you really only need to find one of these.
Then you slap a negative on the other one.
Yes, that'll work too. Or you can integrate from 0 to that. I'm going to call this a for right now, and double it. You know what I mean? A lot of times when your bottom deal here is 0, it's easier to plug it in. So if you think about that, if this has symmetry to it, you can integrate from here to here and just find this, because this is the same. You just double it. Just stick a 2 out on the front, double it at the end. That's what I like to do. If I can ever get a 0 going here, I try to make that happen. It's just easier to deal with.
Okay.
So that's what I'm going to do.
I have a question.
Yep.
How do you store that X value?
I'll show you in just a minute. But I am going to put a capital A here because that's where I intend to store mine, is in capital A.
So if I integrate with negative x to x, it's those two points.
That's true. You don't have to store it if you don't want, but you may want to in some future thing. So once you find x, he's right. You can just integrate on your home screen from negative x to x. But if you don't have symmetry and or you want to integrate, I don't know, say the whole thing's been moved off the origin and you have to find those two, this is how you store it. You go back to your home screen. I've got, notice what I've got right here. I found my intersect on the right side. I've got a positive one. Okay, so I'm going to go back to my home screen by going second quit, and I'm going to type the number x. I'm just going to hit x and hit enter. And it's that same one that I just had because that's the most recent entry in the mailbox x. Now I'm going to store that. I'm going to go store the answer that I just got in A. That's what I'm going to do. And if you hit enter and it types that same number again, then that's now what's in mailbox A. So now X mailbox has that number, and so does A mailbox. And any time that you type in X, as long as you don't change anything on the graph, you don't do anything messing around with the graph at all, because every time you move your cursor or your trace key or whatever on your in there, whatever you went to is now in the X mailbox. But A is stuck with this number until I purposely change it. Okay, so I'm going to integrate the cosine, or 2 cosine x minus the parabola, which is x squared minus 1 dx. I'm going to integrate that from 0 to a, and I double it. That's what I'm doing personally. So I go to the math 9 and start filling in those details. I go 0, and then, whoops, I hate doing this because I'm not very good at it. 0 to, and I'm actually going to type in A, and it will remember what it is. 2 cosine. Close it. Minus parentheses x squared minus 1.
When you visit it, oh, you have to times it by 2.
I get nearly 2.5. Is that what you're getting? Oh wait, I got to double it. I get 4.99. Yeah. Okay. Now, if you want, you can still find just this one and depend on the symmetry. And you could say you could put this one. You could put negative x in A and positive x in B. Store both of those and then integrate it directly without this 2. That's a possibility too. You have to store 2 things. Y'all familiar on how to use the storing then?
Yeah.
Okay. Next question, example 4. You may want to mark this. This one, there's one very, very much like this. Not exactly, but very much like this on your next quiz and your next test. And more than half the people miss it every time. Oh, so don't be one of them. Okay, so this next example, I want you to look at it with me here. It says example 4 says find the area of the region R in the first quadrant without telling you they are giving you a boundary. When they say in the first quadrant, they mean that it has to be above the x-axis, that's a boundary, and it has to be to the right of the y-axis, that's a boundary. So when they say a particular quadrant, you need to pay attention to that because those are restrictions on the area. So it says, find an area region in the first quadrant that is bounded by y equals root x, above by y equals root x, and below by the line y equals x minus 2. And it looks like there's only two equations there, but there isn't. There are three. There is the x minus 2, the root x, and the line y equals 0. Because that put this in the first quadrant. And that's where everybody screws it up. They think, oh, I got two equations. I see the graph. I'm just going to take the radical minus the line. Can you see how that will give you the wrong answer?
Yeah.
Do you understand why that will give you more?
Because it'll slap that negative stuff in there.
And you'll be dealing with a non-function. Well, no, you won't be dealing with a non-function. Yeah, it'll slap that negative stuff that's below the x-axis and still above the line. It will put that in there as part of it as well, if you just do those two regions. So how can we do it to find what we need? Take a look. I could just do an integral from 0 to 2 of root x. That would give me the A region. Because that's still area under the curve. One curve, area under one curve. Between the curve and the x-axis, I could do an integral from 0 to 2 of just root x. Does that make sense? Then I could do an integral from 2 to 4 of root x minus the line. Because that would give me the B region.
Could you just absolute value the second one, the length?
Nope.
No.
Because it will, if you do that, it will flip that bottom one up and paint over what you've already painted in A and still give you the extra area.
Okay.
So you need to split these regions up. If they restrict you to a quadrant, you've got more than two equations. You've got more than two things to consider. It's not just going to be the top one minus the bottom one. Even though it dominates through the entire region from 0 to 4, you will, by doing that, you will get that triangle at the bottom created by the line that's below the y-axis, or the x-axis, if you're not careful. So the idea here is to do it region by region, and sometimes you will have to find out, how far am I going to go? You got to find out where that line crosses the x-axis, because that's how far it would go before we introduce the line. So anyway, they show very clearly on the graph that it's a 2. So to find this one, the area that they're asking us to find, you would do an integral from 0 to 2 of just root x. That's the A region. And then you would add on the integral from 2 to 4 of root x minus the line, which was what?
X minus 2.
You see why it has to be this way? To get the region that they want in the first quadrant only.
Yeah.
Okay, good. We are going to revisit this thing 2 more times before we're done with this section, this very problem. And you will be quizzed on it and tested on it. You'll see the reason why it's important to come back to this. Okay? So I assume that you could do those. I'm not going to waste the time to do these integrals. You can do them on a calculator, you can do them by hand. They're pretty easy things, right?
Yep.
Okay. What's important is that you put it together right so that you're doing 2 different regions. Okay, now, on page 393, where it says integrating with respect to y, this is where it gets weird. This is where you're going to have to make some adjustments in your own mind. And I won't be able to see if you've made them properly. I won't even be able to ask you very many questions to see that. So if you are having trouble or you don't see it the way I see it or the way I'm trying to explain it, please stop me and let's talk about it. Everything that we've done so far with Riemann sums, finding areas between curves and the x-axis, has been where well, at first we imagined rectangles, and then we had the rectangles, the slices were vertical. And then we added all the areas of those rectangles up. Well, now we're going to make our slices horizontal. As you see right there on page 393, he's got 3 examples for you there. And we are, as you can very clearly tell, we are going to be dealing with some non-functions. Nevertheless, it may be important for some applications to find the area between 2 things from left to right instead of from top to bottom. Okay? In the very first one, now this is where you've got to make the adjustment in your mind. In the very first picture that you see there, we say that F dominates G. How come? Because it's farther right. It's got bigger numbers associated with it to the right than G does. Not because G is negative and F is positive, but because F is to the right. That's like being above, if you're thinking X or vertical, like we have been. To the right means it's bigger. And so we would do right minus left now. But our limits of integration will go from here to here instead of from here to here. This way. Okay, so we got to switch kind of 90 degrees or reflect over the line y equals x or something. It's kind of inverse. It's kind of what's going on. Okay, so in example 5, notice we are revisiting that very, very same problem. They have it drawn slightly different. They didn't split it up into 2 regions, A and B. They just got the one region. Can you see that if I integrated from 0 to 2 along the y with horizontals, I would have just one integral? Some of you are not, and some of you are still studying.
Is this the figure 711?
Yes, figure 711 is just like the figure to the left of it on the previous page, but in that one they split up A and B so that we could integrate across the x. They're suggesting that we do that exact same problem by integrating along the y, and we would have only one integral to do. So let me show you what so I can point to the graph if necessary. We've got the square root coming out like this, and we've got a line coming out like this, and we wish to find this space right here. And what the author is suggesting that we do, if you understand switching gears, instead of integrating with rectangles going this way, we're going to integrate with rectangles going this way, understanding that this is the dominant curve, this is the recessive curve, because this one's further right throughout the entire region, and they cross at this point right here, which is 4, 2. So we will be integrating from 0 to 2. Have I spoken too quickly? Do you understand what we're after? Okay, then the integral becomes the integral from 0 to 2. Now here's the other weird part. What were these equations again? Y was equal to root 2, right? I'm sorry, root x. And the other one was y equals 2 minus x? X minus 2? Yeah. You can't integrate these with respect to x because we're integrating with respect to y. So what do we got to do? Solve them for y. I'm sorry, you're right. Solve them for x. So this would be y squared equals x. And this one would be y plus 2 equals x.
Oh, no, it would be plus or minus y squared because the bottom part is the negative y squared. But then that's
Yeah, and we're not doing that one. Okay? So your first thing you got to do, if necessary, if they give it to you, y in terms of x is what you're used to, you got to solve it so you got x in terms of y. And then you got to remember, this is the line, and the line is the dominant one. So we would have y plus 2 minus y squared dy. Crazy, huh? Let's see what they got for an area in the previous one where we were integrating like normal. It was 10/3, which is 3.3 repeated. Do this integral. Now, here's another quirky, weirdly strange thing. These are all written in terms of y. Could you write yours in terms of y too, and so that it doesn't spook you, or do you want to change it to x, and does that bother you?
Well, like if we did it in the calculator, it would be fine.
Right, and if you want to replace all of these with x's, it would be just fine. It would find the same space. It would be okay. If that bothers you and you're worried about it, go ahead and use y's. Use your alpha key and use y's. Just make sure you put dy in the box here, not the x. It's up to you. If you like the y's and the way they're printed, you can use the alpha y. Just make sure that you write it in terms of y and you also dy it. That are the same variables. So I'm going to just switch mine to x. So I'm going to go math 9. I'm going to go from 0 to 2. And I'm going to use x's.
George.
Voila. So we do get that area, and we did it with just one integral if we integrate along the y. Because the reason why it works if you do it just one integral here, because this one, if you remember, right dominates left. This dominates this one throughout the entire region, meeting the hypothesis of the original curve, or the original definition. And we go from 0 to 2 because that's all the farther we're going up for our horizontal slices. But you got to do this little trick because it's got to be written in terms of y. Crazy. Take a look at the next page. Example 6 says making the choice. What are you going to do? How are you going to do this? Because now you can integrate with respect to y and also integrate with respect to x. Here's what it says in example 6. Find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. So the way that they are offered does not make the decision for you. One of them is y in terms of x, the other one's x in terms of y. And if you want to see the graph so you can make the decision based on the graph, you're going to have to solve the other one for y first. Because your calculator only takes them in as functions. So let's pretend that they did not provide you with a graph, the two graphs to the left of example 6. They didn't do that. They just had to do these two equations. It says find the area between them, and you had to graph them. Then we've got a little bit of algebra to do before we can even graph and see what they look like. So let's see if we can produce that graph on our calculator. We have y equals x cubed. That's an easy one. So I'm going to go to my y equals and clear them out. X cubed. And then I've got to do some work on the other one. X equals y squared minus 2. That's x plus 2 equals y squared. I'm solving for y so I can graph. So that would be plus or minus the square root of x plus 2. And you're going to need them both. This is what I'm talking about. Sometimes we integrate non-functions. And so I'm going to write down the square root of x plus 2. And then in y3, I'm going to write negative bars, y bars, function y2, because I just want the negative aspect of this. You don't have to do it that way, but that's what I'm going to do. And then I'm going to go zoom standard and see where I'm at. That gives me a region that's obviously lopped off by those, but I can't, I'm going to scoot it in. I'm going to go from -3 to 3 and from -2 to 2. And if I do that, if I squeeze it down a little bit, it gives me a little better idea of where it's lopped off. Right? And clearly the red and black one are supposed to be considered together, and they are a non-function. But together, they also take this cube function and lop off a very strange looking region. Now, if you wanted to integrate this thing along the x-axis, I'm going to put this on the board too. I'm looking at this region right here. To integrate this along the x-axis, I would have to find this, and I would have to integrate this curve minus this curve from -2 to that region right there. That would give me that right there if I did that. And then this dominates this throughout the rest of it. I'd have to integrate from here to here, wherever that cross point is, this curve minus this one. Would that work? Yeah, I think it would.
I'm confused. Why did you have to lop it off?
Because the way this comes around here is a non-function, and I've got to figure out a way to find this area right here. I suppose that I could integrate from here to here underneath this curve and double it. We could do that, and then integrate from this using this curve minus this curve from here to here. That would work too.
But wouldn't if you integrated that little piece to the left, would it just cancel itself out?
You could integrate.
No, not if I integrate from here to here underneath this curve and double it. That would double the area and give me this little piece right
So
here.
it's whole painted space, it's not.
Yeah, it's
Yeah, it's painted space.
Okay.
Area between the curves. Area. We're talking area here.
Okay.
Or we could find this y value right here and integrate from there to this y value, this curve minus this one. That's what I prefer.
you could just do the whole thing, right?
Yes, in one integral.
As well. Okay.
So I'm not going to consider this one anymore. Instead, I'm going to find out the y values where these intersect points are, integrate along the y from that lower one to that upper one, this curve on the right, which is the cubed curve, minus this curve on the left. But I need them x in terms of y to do it. So I already had this one right here, x in terms of y. That one's already, they handed it to me. And this one was y equals x cubed, and so x is going to be the cube root of y. That's its y value. It's y solving. And it is the cubed function or the cube rooted function here. It's that one that's fully to the right of this one. Now all I got to do is find these two section right there.
I found the first one.
Okay.
Pretty nasty.
So I go to my graph and I go Calc and intersect. I'm gonna find the lower one.
We're trying to find the y value, right?
Yes. And so I get that this point right here is -1, -1. This one right here.
Yep.
So this is -1. That's the part of it I'm interested in. Now go up and find the intersect of the other one.
How do you store the y? That's it, it's just-
I get 1.214, blah, 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 blah. No, I get 1.793. That's what I'm interested in.
Yeah.
So this is about
How do
1.793.
you store
That's
that?
approximately that. I'm going to store that in B,
How do you store that?
just like you do X. It's just that there's not an X key dedicated to it. So now, if you found that one last, and it's the irrational one, you go second quit, you go alpha 1, because that's where Y is, and hit enter. It'll bring that Y value back that you just had.
Okay.
And then you go store in Y is what I'm going to do. It was already Y. No, actually, I'm going to store that in B. I'm going to store it in B. Store in B. Okay, so I've got 1.7930033715 and so on. I have that stored in my B. So now I'm going to integrate from -1 to B. Let's see, the cube root 1, minus the parabola.
But we need to get one of them into. Oh, we already did.
That's what I did right here. This one was handed to me this way. This one was pretty easy to do. I just had to cube root both sides. Okay, so see if you can find that.
Ooh, great heavens.
You said y already. Okay, so alpha and then 1
I get 4.215 basically.
That's what I got.
That's what I got.
4.215.
You got it.
We're able to do it with one integral. This one would have required quite a bit of finagling. We'd have had to do this one from here to here, double it, and then integrate this minus this from here to here. You could have done it. It'll work. And I can follow them both. It's whatever you choose to do. But integrating along the y can sometimes be easier. Don't forget, you got to solve each equation for x in terms of y. Now, I want you to look at the exercise. Oh, no. One more revisiting. Example 7. Same problem again. This is the one that I really like this method. Because the area that's determined between the curve and the x-axis is determined by the line is just a triangle. So what I could do is I could integrate along the x from 0 to 4 underneath the radical, and then just subtract the area of that triangle, which I could find. I've been able to do that since 2nd grade. That's another way to do it, if you see it. Do you want to talk more about that? You all understand what's going on there? That's how I would do this problem. Because it keeps me comfortable along the x, and I'm really good at geometry, especially finding areas of right triangles. That's really easy. It's 2 times 2 cut in half, so that's 2. I would find the area under the curve from 0 to from 0 to 4, I'll find the area under the front x, and then subtract 2 from it. All right. I want you to look at what you're doing, 395, the exercises at the bottom of the page there. They got 6 problems. They got the graph already drawn for you. I want you to notice in the first one that they give you both equations, y equals and y equals. That means they probably want you to integrate along the y. Along the x, because they give it to you in normal form. Take a look at number 2. They've given you y equals and y equals. Chances are they want you to integrate along the x-axis. And if it were me, I would integrate from 0 to 5/3 and double it. See? You got symmetry going? Okay. Notice in example 3, or exercise 3, they give both equations, x equals. Guess what they're encouraging you to do? Integrate along the y. Okay?
Which
Look at the next one.
Which one's the rightmost one on that one though?
Y squared.
Okay, that's what I
Y
thought.
squared. Okay, in number 4, they give you x equals and x equals. Again, I think they want you to integrate along the y. Number 5, they give you y equals and y equals. Again, you see the origin symmetry. I would integrate from 0 to 2 or double it. And then in number 6, they give you y equals and y equals again. The symmetry at the origin, I would integrate from 0 to 1 if it were me. Okay, so if they give you x equals something with a y in it, they're trying to get you to integrate along the y, and they've already provided you with the equations in the right form. You should do that instead of trying to bend it to your will, because you're sorry. Anyway, this is all about integrating between curves, sometimes along the y, sometimes along the x. Good luck. We'll work on this tomorrow together. See ya.